When we evaluate an integral by trigonometric substitution, we have three different scenarios we need to consider. In the first scenario, we are given a right triangle with angle theta. The side opposite to angle theta is x. The side adjacent to angle theta is a. And the hypotenuse is the square root of x squared plus a squared. So my substitution will be the following. X over a is equal to tangent theta. Multiplying both sides by a, we get x equals a tangent theta. And then the square root of x squared plus a squared divided by a is equal to secant theta. Multiplying both sides by a, we get the square root of x squared plus a squared is equal to a secant theta. In the second scenario, we have a right triangle, right here, with angle theta. The hypotenuse is x, and the side adjacent to angle theta is a. So by the Pythagorean theorem, the side opposite to angle theta is the square root of x squared minus a squared. And so my substitution will be as follows. X over a is secant theta. Multiplying both sides by a, we get x equals a times secant theta. And then the square root of x squared minus a squared divided by a is tangent theta. Multiplying both sides by a, we get the square root of x squared minus a squared is a times tangent theta. And in the third scenario, we have a right triangle with angle theta. The side opposite to angle theta is x. The hypotenuse is a. And then the side adjacent to angle theta is the square root of a squared minus x squared. So my substitution will be as follows. Based off this right triangle, x over a is sine of theta. So multiplying both sides by a, we get x equals a times sine of theta. And then the square root of x squared minus a squared divided by a is cosine theta. Multiplying both sides by a, we get the square root of x squared minus a squared is a times cosine theta. And with that, we can look at some examples. The directions say to evaluate the integral. And so in example 1, we have the integral of x squared over the square root of 9 minus x squared dx. And if it helps, we can write this as the integral of x squared divided by the square root of 3 squared minus x squared dx. So in this example, notice that a is equal to 3. And if we go back to our scenarios, it looks like it fits scenario 3. And so if you notice, the hypotenuse is 3, right? I have a right triangle with angle theta. The side opposite to angle theta is x. And then the adjacent side to angle theta is the square root of 9 minus x squared. And so based off this right triangle, I can make my substitution. And so x equals 3 sine theta. Dx is 3 cosine theta d theta. And then if I square both sides, notice that x squared is 9 sine squared theta. And then based off this triangle, the square root of 9 minus x squared is 3 cosine theta. So my overarching goal is to transform this entire integral from an integral in terms of x to an integral in terms of theta. And that's exactly what I did. The integral of x squared over the square root of 9 minus x squared dx is equal to the integral of 9 sine squared theta over 3 cosine theta times 3 cosine theta d theta. So I'm going to pull the 9 out in front, and then notice how these 3 cosine thetas end up disappearing. And so I get 9 times the integral of sine squared theta d theta. which is 9 times the integral of 1/2 times 1 minus cosine 2 theta d theta. I'm going to pull the 1/2 out in front as well. And so this is 9/2 the integral of 1 minus cosine 2 theta d theta, which I can do. It's much simpler than our original integral. So this is 9/2 times the quantity theta minus 1/2 sine of 2 theta plus c. But remember, sine 2 theta is equal to 2 sine theta cosine theta. Okay, so this is 9/2 the quantity theta minus 1/2 of 2 sine theta cosine theta plus c. The 2's cancel. And so I get the following. Now, let me backtrack one quick step. Remember that sine of theta is equal to x divided by 3. Solving for theta, we get arc sine of x over 3. And that's what I get for that first term. So I get 9/2 the quantity, arc sine of x over 3. And then remember, sine of theta is x over 3. Cosine theta is square root of 9 minus x squared over 3. And so notice when I multiply the numerators and multiply the denominators and draw a division bar in between. And so that's where I get that second term from. So notice that I get 9/2 the quantity arc sine of x over 3 minus x times the square root of 9 minus x squared over 9. 3 times 3 is 9, plus c. And then I would leave it to your instructor if your instructor wants you to distribute the 9/2 to each term within those parentheses. That's example 1. So let's take a look at example 2. Suppose I had the integral of the square root of 1 plus x squared over x dx. So I drew a right triangle with angle theta, right? My 90-degree angle is here. The side opposite to angle theta is x. The side adjacent to angle theta is 1. And then the hypotenuse is the square root of x squared plus 1. So x is tangent theta, dx is secant squared theta d theta. And then the square root of 1 plus x squared is secant theta. And so the integral of the square root of 1 plus x squared over x dx is equal to the following. It's the integral of secant theta over tangent theta times secant squared theta d theta. But remember, 1 plus tangent squared theta is equal to secant squared theta. So we can write this as the integral of secant theta over tangent theta times 1 plus tangent squared theta d theta. And then what I did was distribute the secant theta over tangent theta to each term within those parentheses. And when I did that, I got the integral of secant theta over tangent theta plus secant theta tangent theta d theta. Now, this next line may not be as clear, so I'm just going to give you a little bit of side work here. So if you have secant theta over tangent theta, okay, I claim that's cosecant theta because I could write this as 1 over cosine theta divided by sine theta divided by cosine theta. But these guys are going to go away. And what you get is 1 over sine of theta. And that's where the cosecant theta came in. So it's pretty neat. Now I can integrate nicely. And when I do, I get the natural log of the absolute value of cosecant theta minus cotangent theta plus secant theta plus c. Now, redrawing that triangle, notice I redrew it from the other page. I have a right triangle with angle theta. The side opposite to angle theta is x. The side adjacent to angle theta is 1. And the hypotenuse is the square root of 1 plus x squared. And remember, cosecant theta is the hypotenuse divided by the side opposite to angle theta. And that's where I'm getting the natural log of the absolute value of square root of x squared plus 1 over x. And then cotangent theta is 1 over x, adjacent over opposite. So once again, I get the natural log of the absolute value of the square root of x squared plus 1 over x minus 1 over x plus secant theta, which is the square root of 1 plus x squared plus c. And then on the very last line, I just wrote it as the natural log of the absolute value of the square root of x squared plus 1 minus 1, all divided by x, plus the square root of 1 plus x squared plus c. And let's take a look at example 3. And I picked this one on purpose. It's a really interesting couple of examples. Let me backtrack just a little bit for you here. Notice how we have the integral of the square root of 1 plus x squared over x. And notice what I did. In the third example, instead of the integral of the square root of 1 plus x squared over x, I have the following. I have the integral of x over the square root of 1 plus x squared dx. Now, you can do this by u substitution. That's fine. You can do this by a trigonometric substitution. That's fine, but a u substitution is cleaner and faster. It's just that subtle difference. And so here, I'm going to let u equal 1 plus x squared. du is 2x dx. X dx is 1/2 du. And it's a really clean problem. It's 1/2 the integral of 1 over the square root of u du, which is 1/2 of 2 square root of u plus c. 2's cancel, and we get the square root of x squared plus 1 plus c. It's a great question because side by side, in the second example, we did a trigonometric substitution when the integrand was written, when we did the integral of the square root of 1 plus x squared over x. And just that little switch, we were able to do this by u substitution. So, in example 4, we have the integral of 1 over the square root of x squared plus 2x plus 5 dx. But I'm going to rewrite 5 as 1 plus 4. That's legal. And so we get the integral of 1 over the square root of x squared plus 2x plus 1 plus 4. And if I group off these first three terms, that's a perfect square. And so I could write this as the integral of 1 over the square root of x plus 1 squared plus 4 dx. Now, you don't have to do a u substitution. You can. So in other words, I could let u equal x plus 1, and then du is dx. And we could look at the integral of 1 over the square root of u squared plus 4 du. And that's fine. But you don't have to, technically. Instead of labeling the side opposite to angle theta x, I labeled it x plus 1. The side adjacent to angle theta is 2. And then the hypotenuse is the square root of x plus 1 squared plus 4. So you don't always have to do a u substitution if if you're able to handle it with, instead of being an x, it's an x plus 1. And I'm talking specifically for this example. Now, what that says is that x plus 1 over 2 is tangent theta. Multiplying both sides by 2, we get x plus 1 is 2 tangent theta. Dx is 2 secant squared theta d theta. And then the square root of x plus 1 to the second plus 4 divided by 2 is secant theta. Multiplying both sides by 2, we get the square root of x plus 1 squared plus 4 is 2 secant theta. So when we look at this integral, we have 1 over the square root of x plus 1 to the second plus 4 dx is equal to, it ends up being the integral of secant theta d theta, which is natural log of the absolute value of secant theta plus tangent theta plus c. And making my substitution, I get natural log of the absolute value of x plus 1 plus the square root of x plus 1 to the second plus 4 divided by 2, all divided by 2, plus c. And then simplifying a little bit more, we get natural log of the absolute value of x plus 1 plus the square root of x squared plus 2x plus 5 plus c. And so I took advantage, by the way, of this property. So notice that natural log of a over b is natural log of a minus natural log of b. And so when I had the natural log of x plus 1 plus the square root of x squared plus 2x plus 5, all divided by 2, right, plus c. Well, this can be written as natural log of x plus 1 plus the square root of x squared plus 2x plus 5, right, minus natural log of 2 plus c. But minus the natural log of 2 plus c is still one big fat constant. So, okay, that'll do it for this video. It's on trigonometric substitution for a Calculus 2 class. Okay, thank you.